Yeah, welcome everybody to the first edition of the Quasiworld seminar for this academic year. So, well, one of our organizers will be a speaker today, and then I guess one of his students. So let me give the word to Sylvester, please.
Thank you. It's a pleasure to speak here. I checked that, I think when we started, it was like the third or fourth talk of the seminar that I gave. So by now, is it 3 or 4 years ago? So it's nice actually to have the opportunity also to speak here again and to have something nice to talk about, namely this work that I've done with Riku, and also I'll mention some work with a guy on this on the combinatorial Loewner spaces, and a question about when they're quasi-symmetric to Loewner spaces. So in this seminar, of course, hardly one has to define this, but just as a reminder, so I say consider a problem of the conformal gauge. So this consists of all metrics d prime that are quasi-symmetric to D. And this quasi-symmetry relation can be described, there are many equivalent ways, but I describe it in this fashion, that balls in one metric are roughly balls in another metric. So if I take a ball in the D metric, then this will resemble a ball, be contained in a ball, and outside contained in a larger ball. And well, I should be specific here about the radii, that the radii here on the outside are comparable. So given the same ball here. So on the outside there, these are inflated by a certain radius. Weak quasi-symmetry would be this condition just with k equals 1, but the quasi-symmetry condition is equivalent this for all k. So you get this equivalence class of metrics, and this equivalence class is called the conformal gauge. And this is quite massive, as anybody who has worked with these notions knows. There are a lot of different metrics here. So as a concept, it's a bit unwieldy. So what one might want to do, and I'll motivate this more in a second, is that we want to find a canonical metric in this conformal gauge that in some sense is nice. And I will give some definitions of what this nice could mean. And ready to spoil a little bit the punchline, but also to tell you what this is all about and what the main result will be, is that there was a conjecture that self-similarity combined with this combinatorial Loewner property, the condition, which is here in red because I haven't defined it yet, but you'll have to wait a second for the definition. This is sufficient for very nice metrics to exist. So it gives an affirmative answer, at least to a certain interpretation of this general question, is are there canonical good metrics in the conformal gauge? And our main result with Riku says that this conjecture, at least as stated, is not false. So there are counterexamples which are approximately self-similar. Combinatorially Loewner, this CLP condition is throughout this talk abbreviated as CLP, in case you wonder, and which are not nice. And this nice will involve a notion called the Loewner condition, which I will also define shortly. But we'll see this result again, but this is the gist of at least a big part of what I will talk about. So what I mean by nice, I will give a few examples. I mean, these are examples from the Quasiworld. Also, a lot of the people from this seminar. I don't know if Daniel is here presently, but so the first one is the geometric problem example, just a simple toy example, but also has appeared in the literature. So here you have a self-similar fractal that's can be constructed by an iterated function system in R3. And it's pretty clear what is happening here. So you start off with a cube, you take its face, you subdivide it, and then these squares, at least some squares in the center, you take the bottom squares off and glue this cube minus a face to it. And by this process, you get a surface with a cubical subdivision, and then on each of these faces of this cubical subdivision, you repeat this process. So this gives you a fractal sphere, so a metric on the sphere, or something homomorphic to the sphere. And if you compute it, its Hausdorff dimension, for example, is strictly greater than 2. I don't want to compute it now. And if one looks at the conformal gauge of this thing, you could ask, well, so what is my nice metric in this case? Well, in this case, the nice metric turns out is the usual sphere. So this metric, this space, is quasi-symmetric to the standard sphere. This is Daniel Meyer's result about snowballs. In fact, the quasi-symmetry can be realized by a quasi-conformal map of the R3. Okay, but so this is a toy example. I mean, of course, great. We can recognize that this funny space is actually quasi-symmetric to the sphere, but why do we care? And there's a few motivations. So I'll again steal picture. These are all stolen from people's papers, and some people are present here. So this one is from Mario, Annina, and Misha, and this one's also a talk in the seminar. I think was it? Well, I don't exactly remember now anymore when it was, but some time ago. So in complex dynamics, there are these combinatorial constructions of expanding Thurston maps. So here is one example, and this can be visualized as here, every one of these squares, this map L is scaling them to one side of this pillow space. The pillow space here is just two squares glued together. And the coloring there, black and white, indicates which side of this pillow the things are glued to. So this map on the left is a combinatorial description of it, and one can ask whether this can be realized or is equivalent in a specific form sense with a rational map. But why I mentioned this here is that on the left here, you have a fractal-like object, a fractal-like space. So just like in the cube case, you can imagine that you repeat this process. It's almost the same, except that you have to do a slightly different thing for the white and the black pieces, but it's still a self-similar construction of a fractal that's in Mario's and Daniel's book is called the visual sphere. And the fact that in this case, for this sphere, that this lattice type map is realized by a rational map is equivalent to the problem that this fractal that arises on the left is quasi-symmetric to the usual sphere. So this equivalence problem actually in this fractal language is a question about whether a certain metric space or certain conformal gauge contains the spherical metric. Okay, so this is obviously an interesting question and a difficult question even in many simple examples, as one can see from there, Mario's, Annina's, and Misha's. Nice work. Well, let's go on. So that was why, if you are doing complex dynamics, why you might care about existence of a nice metric. But if you're doing analysis on fractals, so by this I mean some sort of potential theory or studying questions about Dirichlet forms or on spaces. So you can take this Sierpinski gasket and there's a construction of a Dirichlet form on this space that goes back to Kuzuk and Zoe. You could add, so this Dirichlet form gives you also an associated Sobolev space theory. And this question of a nice metric actually becomes whether we can recognize, or one interpretation of this nice metric question becomes there, that whether this function space that we constructed can be identified with something that is more familiar. So, and it turns out that in this case, in the Sierpinski gasket case, this can be identified with a more familiar space, namely a Sobolev space called the Newton Sobolev space, or the metric space Sobolev space of Shanmugam. But after the space has been deformed by a metric, and it's called the resistance metric, and the measure has been changed so on the right here you see this is called the harmonic gasket. So in this case, the deformation changes the potential theory in a way that gives us more tools to analyze the potential theory. Okay. It also helps us in studying random walks and understanding what's really happening there. Okay, so there, the nice structure is where this function space becomes more understandable. And finally, there's a third reason why one might care about these is from geometric group theory. And here, what I've drawn is essentially the fundamental group of a surface with two holes. So the fundamental group is identified with the cells in this image, and the dual graph of these gives you a realization of the Cayley graph of the fundamental group of this manifold. And what you also see here, so this is that this fundamental group, it's a quasi-asymmetric, so it's a dense subset, so every point is at a finite distance to the hyperbolic plane. The limit set here, which is now just S1, it can either be thought as the boundary at infinity of the hyperbolic space, or it can be thought as what is called the Gromov boundary of this group. But although this one-dimensional example is not really the best, because one-dimensional cases actually tend to be a little bit boring, so the higher dimensional cases are much more interesting. But in this case, if you take, there are two different constructions of a metric here. So if you think of this as the boundary of the hyperbolic space, then there is the construction of a cat minus one, just the constant negative curvature metric and its Gromov boundary. And with this metric, the boundary becomes one-dimensional, our usual S1. But if you take this group perspective and you construct a metric using that theory, so there's a construction of a visual metric also in that case, then you don't get the S1 metric. In fact, you will always get something that is alpha alphas regular with alpha strictly bigger than 1. So it will be some kind of a snowflake curve. The size of an interval will be comparable to, the diameter of the interval to the power alpha. So in some ways, the nice metric in this case is the cat minus one metric, the S1 metric. And now the group visual metric is actually a snowflake, so it's less nice. But as said, the one dimension, this is a gross simplification, because in one dimension, it's really not, there are quasisymmetric maps behave oddly in one dimension, or they're, for example, they're not absolutely continuous. But this becomes more interesting in higher dimensions. So you can construct, for example, three-dimensional buildings whose boundaries consist of spheres. And in those cases, these questions become much more interesting. And it's not always trivial even what metric is natural. So if you've heard of Gordon-Pajot buildings, in those cases, the cat minus one metric is not natural. You have to actually use some other metric to construct. So it's a non-trivial task to construct this canonical nice metric. Are there any questions or comments or thoughts at this point? Okay. And of course, goes without saying, since we talk about quasi-conformal geometry, that there's a long-standing conjecture of canon about whether groups whose visual boundaries are homomorphic to the standard sphere, whether there are actually quasi-isometric to isometry groups of the hyperbolic 3 space. This problem is also a question about whether there's by the work of Mario and Bruce Kleiner, this is equivalent to a question about whether there's a certain nice metric in the conformal gauge of the visual boundary. So these are very difficult questions, actually, in general, because, well, they're open in many cases. But so in all of these cases, I mean, in some of these cases, we can answer this problem and we can identify it. The question is, when does a canonical nice metric exist? But what does this mean in a specific sense? And there are different senses of nice, for sure. But it turns out that actually in many cases, these are equivalent. And some classical ones that I will focus on is that in some sense the metric is optimal. So we have some functional measuring the size, and Hausdorff dimension or Hausdorff measure is one nice way of measuring the size of the space, and we might want to choose the metric that makes this Hausdorff dimension and consequently also the Hausdorff measures as small as possible. So that's one way of thinking. We want to find we've defined a functional and find its minimum or determine if the minimum is attained. Another thing is that we might want some nice properties from this metric, and in particular because one property that one wants is some sort of first order analysis. So by work of Heinonen and Koskela, Shanmugaling on Chiger, what this boils down to is some sort of Poincare inequality, or in this talk I will focus on the Loewner condition, which also is a natural condition to look for because we're talking about quasisymmetric maps, and the work of Heinonen and Koskela was specifically about how do quasisymmetric maps behave in Loewner spaces. And that was really what started analysis on metric spaces in many ways. So that's kind of canonically nice to look for. It also gives you a nice tool to study quasisymmetric maps, because once you have a Loewner metric in the conformal gauge, what you can, for example, try to do is you can try to differentiate quasi-conformal maps between spaces. So in certain cases, you can define a differential, and that differential can tell you a lot about this function. That's not all of the cases. I'll just mention that I won't really talk about this in this talk, but there's a notion extensively recently studied by Murakami Kajino, also Ryosuke Shimizu in the audience, and Jun Kigami, his work has touched upon this, is this potential theory framework that I briefly mentioned. And there is the search for a nice metric can be thought of as a search for a metric with nice parabolic Harnack inequalities, or what's then called, what leads to a notion of a conformal walk dimension. But that's an entirely different thing. So yeah. And in some cases, actually all three of these coincide, but I will focus on the first two of these, 1 and 2. Okay, so let's define these more rigorously. So the conformal Hausdorff dimension, as I mentioned, is a certain optimization problem where we're looking for all first regular metrics. And these are metrics where the Hausdorff dimension of the space, so this is the Hausdorff measure, but Hausdorff dimension of the space behaves scale invariantly like a Q-dimensional space. So Hausdorff Q measure of the ball is proportional to the radius to the power Q. I'm usually working on compact spaces, so hence the diameter bound here. The all first regular conformal dimension is the infimum of all the over all the metrics in the conformal gauge that are Q all first regular for some Q of the Hausdorff dimension, but for Q all first regular spaces, this Q is equal to the Hausdorff dimension. So you infimize over these Q such that you have an all first regular Q all first regular metric there. Okay. Of course, the natural question is then, is this always finite? So because your metric might not be all first regular to begin with, but under mild conditions, say if you are uniformly perfect and your metric space is doubling, then actually it always contains a metric that is all first regular in this conformal gauge. So you can do this minimization problem. And well, this notion has also been talked about in this seminar, and there are different definitions about this. But I'll mention one thing before going on. So last year, I showed a result that all the different definitions at conformal dimension agree. So whatever definition of conformal dimension you've learned, they agree with each other, at least under fairly mild assumptions that will be the main focus of my interest here today, namely arcwise connected spaces that are self-similar in some sense. So this includes everything like the Sierpinski carpet, all you manifolds, all Euclidean spaces, all the Carnot groups, etc. So a gigantic amount of examples. And in all of these cases, all the possible definitions of conformal dimension are the same. So for this reason, if you've learned another definition, you can disregard it now and just focus on this one, or you can, yeah. Great. So this is the optimization problem, but a perceptive listener will notice that. So there's this infimum here, and this infimum may or may not be attained. It might not be a minimum. And the question about whether there is a nice metric in terms of this problem is that, is there a metric that makes this infimum a minimum? Is there a metric that is Q alphas regular with Q equal to the alphas regular conformal dimension? No. So there always exist metrics that approach it, but perhaps there is some odd degeneration that prevents you from taking a limit, or that the limit is actually not a metric anymore, or blows up anyway. Okay, so this is the attainment problem, and this is one way of asking, does there exist a nice metric? The other way was looking for some nice analysis. And you still, for this nice analysis, you still put this alphas regularity condition. So that stays. But what you add instead, you don't minimize the Hausdorff dimension, but you add this nice analysis condition. And this nice analysis condition can be thought in many ways, but it is some sort of scale invariant measure of having a lot of curves at all scales and locations. So parse this a little bit. So this is a condition for all pairs of continua E and F. So E and F are connected compact sets that are non-degenerate. So the diameters are positive. And then the scale invariant measure of distance is you take the distance between them and then you divide them by the smaller of the diameters of E and F. I mean, this essentially focuses on the case when E and F are roughly the same size. So it's just the distance divided by the diameter in that case. And we're looking at all the curves that go from E to F. Gamma. All the rectifiable curves that go from E to F. And we insist that a quantity called the conformal modulus, or Q modulus, of this curve family is bounded from above and below by something that depends on the relative distance between E and F. Technically, people who know this upper bound here is not really needed, but I'll add this just to make this condition to look symmetric and to make it look similar to what is later seen. So this upper bound is implied by the alphas regularity, so that's why it's not really needed in the statement. The lower bound is the substantive one. But so what is this quantity? This is given by this optimization problem. So if you've seen this, you know already, but if you haven't, I want you to focus on two things. There's the functional that we're optimizing is the Q integral of rho with respect to the Hausdorff Q measure. So that's the measure I'm implicitly using here. And then there's a condition for all curves that the curve integral of rho is bigger than 1. So minimizing integral over curves is at least 1. So, yeah. Okay, so the Loewner space, you have this condition, and then this allows Heinonen and Koskela we're able to use this condition then to prove, for example, the statement that quasi-conformal maps are equivalent to quasisymmetric maps and lots of other regularity statements. Okay, so in terms of this Loewner condition, the combination of these two things, so an alphas regularity and the bound on modulus, the question becomes, does there exist a Q Loewner metric? And just one thing, so it might be a little controversial that to the Loewner condition, I add this alphas regularity condition, but I add it here because the Loewner condition becomes really only useful, in my view, if you have the alphas regularity. Because if you don't have alphas regularity, Loewner condition is not scale invariant. But with the alphas regularity, it's a scale invariant condition. So in my view, at least in isolation, the modulus bound is not so useful. So that's why Q Loewner, I should be both. But yeah, but at least if you disagree, then it's just for this talk. Yeah. Okay, so we have these two problems. One is the attainment problem. The other one is is the space quasi-symmetric to a Loewner space, or does there exist a Q-Loewner metric in the conformal gauge? And these look different, but the good news is that these are actually equivalent for this mystical class of QCLP spaces, Q-combinatorial Loewner spaces. And this fact, I mean, this was implicitly stated in many places. For example, Mario's and Bruce's papers talk about this, at least have strongly implied that something like this is true. Heinonen just falls short of saying this is true. But since nobody had actually said it out loud, then I and Jeff Cheeger, we wrote this in one of our papers. We wrote this out. But really, the arguments were there. So it should have been known. The reason is, in short, that when you are Q-alpha regular, the discrete modulus is this condition that involved in Q-combinatorial Loewner condition is just equivalent to the continuous one. These two notions that come up are comparable, but that's only if you're at the conformal dimension and your Q-alpha is regular. Another thing to say is that actually from these one way is classic as a bit older. There's an argument of Tyson. Also, Pansu had a version of this argument. And this other argument requires the comparability of the notion of discrete modulus and continuous modulus. Right. Okay, so these two problems are equivalent, and so either one of them is a very natural, nice thing to look for, but fortunately they're not different. But these are both very difficult questions. So I mentioned Heinonen's conjecture, but even in like most practical cases, we don't understand them. So I show here 3 columns, and this is a caricature of our state of knowledge before this summer. So on the left here, these are spaces where we know that they are Loewner because we have given them a Loewner metric. So we have the standard sphere, we have the Heisenberg group, and then we have a thing called the Bourdon-Pajot building. So in these cases, okay, Bourdon-Pajot, it's not trivial. It's not trivial how to construct the metric, but once you've done it, then all of these become trivial because we know what the metric is. We know what the Loewner structure is. Okay, so there's not really a question of do you have to deform it in some abstract way. Then there is a bunch of examples where we can just say no for obvious reasons, for obvious and not interesting reasons, namely Cantor sets, which are disconnected. The space has to be connected to have any curves. This condition will involve curves. And then another thing is spaces with a lot of cut points. And in these cases, the cut points allow you to do a proof that this conformal dimension is actually equal to 1, but it's not attained for just purely topological reasons. So, okay, so we know some spaces are Loewner because we have the metric at hand. We know some spaces are not Loewner because they fail to be so for stupid reasons. And then there's all the rest. There's all these other spaces, the Sierpinski carpet, the boundaries of certain Coxeter groups, the Menger curve, the list goes on and on. Almost any given fractal that you will give that doesn't sort of trivially not attain its conformal dimension, this question is either hard or not solved. And I mean, this picture makes these columns look really the same, but I'll draw just another picture very quickly that's saying that, look, there's all the spaces. I mean, this is a really big space, and then there are the cases that we understand. It's a tiny part. So the cases that we understand are isolated few examples, really, compared to all the other ones. So if you just take a random space, a random attractor of iterated function system, we have no clue whether there is this Loewner metric in there. So it's really an embarrassing state of affairs. We have this nice question, and for 20 years we didn't really understand anything beyond those first 2 columns. I mean, somebody might disagree with this assessment, but at least this was my understanding. But despite this, there was actually a very reasonable attempt at a characterization of having this nice metric. And this is what is called the combinatorial Loewner property. And why it is a natural candidate for this characterization. Firstly, the Q-Loewner condition implies the Q-combinatorial Loewner condition. So if you have the metric that is Q-Loewner, then you are Q-combinatorial Loewner. One thing. The second thing is that this one is quasi-symmetry invariant, but this one is not quasi-symmetry invariant. Essentially because the quasi-symmetries can change the Hausdorff measures. So if you're looking for a necessary condition that is quasi-symmetry invariant, that would be true for all metrics in the conformal gauge, this QCLP seems like the perfect thing. And besides, it seems very natural because as you see maybe already from the slide, this looks exactly the same formally. So so let's see. So here, what we have written up here is the Loewner condition. So this was a modulus bound and all-force regularity. Well, as I said, to get the combinatorial Loewner condition, we take away all force regularity assumptions. There is no all force regularity assumption in the combinatorial Loewner condition. We just focus on the first one, and we write the same condition. Okay, I've simplified this a little bit because I wanted to make this look very similar. So this is a slight lie and a slight simplification of the literature, but a LLC space, so a sufficiently connected space, is a P combinatorial Loewner if for a certain notion of discrete modulus, you have the same upper bound and same lower bound as you have in the continuous case. And the trick here is that this discrete modulus, once you drop the all force regularity assumption, it has nothing to do with the continuous modulus. If you have the all force regularity assumption, these are essentially comparable, and that's why you get the equivalence. But if they're otherwise, they're not. Okay. But just to tell you a little bit what this is, so this discrete modulus condition, if you remembered what I said about the Loewner condition, the Loewner condition involved infimizing over an integral. Well, now we're discrete modulus, so a discrete integral is a sum, or a weighted sum. In this case, it's just a sum. And integral over a curve, well, it's discrete sum over some objects. And I'll draw a picture of what this looks like a bit, so you'll see it even more clearly. So we have our two sets E and F, and we're discretizing the space in some way, and these discretizations come from a covering of the space with balls at a certain scale. We have finitely many balls. And this P thing here, what this is a collection of balls where consecutive balls intersect each other, or possibly some inflations of them intersect each other, depends on your definition a little bit, and it's not really relevant how you define it. For all these finite collections of balls that connect E to F, you assume that your function adds up to 1. So discrete modulus bound from above and below in a scale invariant way. Okay, I'm obviously brushing a lot of things under the rug here, but yeah. So this looks exactly the same. So it is very then reasonable to conjecture that actually this QCLP is exactly the right thing. So there's should be a converse to this fact that the Q-Loewner condition implies the QCLP. Converse has to be QS invariant. So you could assume that the Q-combinatorial Loewner condition implies that you are quasi-symmetric to Loewner. And well, there's this is already maybe somewhat obviously at least too much to hope for. So you should only assume this for some together with some self-similarity. And this self-similarity is actually satisfied in all the cases that one would often be interested in this conjecture. Kleiner posed this, Bourdon and Kleiner introduced the notion of combinatorial Loewner in the beginning of 2000s, and then in 2006 at the ICM, Kleiner posed this conjecture. Although in all fairness, I think he may have not always believed in this conjecture so much. So whether it's a conjecture or a question, that's, yeah. So this was open since 2006, and there hadn't been really a lot of progress about this, but what's interesting so just to reinforce an interest in this question is that, okay, there are not so many spaces where we know that they are quasisymmetric to Loewner, or we cannot answer this nice metric question. But this combinatorial Loewner case, there are lots of cases. So there are all these Loewner cases where we know this. There are all sorts of iterated fractals systems. So I'll say, for example, the Sierpinski carpet, the Sierpinski cross, the Menger curve. A gross simplification is that, well, I'll maybe say this soon. So a host of these kind of cubical type fractals, as long as they don't have cut points and for certain degenerate cases. But then also many boundaries of groups, of hyperbolic groups. For example, this boundary of this comes from actually a truncated tetrahedra reflection group in the hyperbolic 3 space. The limit set of this group, which is depicted in the image, is a homomorphic to a carpet, but we don't. This one attains its conformal dimension, but we do know that it's CLP by the work of Bourdon and Kleiner. And what's depicted here above, well, this is just a standard dodecahedron, but in the hyperbolic space, one can construct a right-angled hyperbolic, right-angled dodecahedron, and using this right-angled dodecahedron, one can build higher dimensional generalizations of the Bourdon-Pajot buildings that were studied by Clay. These Bourdon-Pajot buildings are, or they have a Loewner metric that we can actually explicitly describe, but these higher dimensional spaces, there's this work by Antoine Clay, and we have no idea whether they attain their conformal dimension or not. Actually, for most non-trivial groups, we don't really understand it, but we do know that they're combinatorial Loewner. So if this conjecture had an affirmative answer, this would be wonderful because we would suddenly know that all these spaces have a Loewner structure. So that.
Sylvester, can I make a remark here?
Yeah.
Absolutely. Yeah, I just wanted to, I guess, for people who weren't around at that time, just to give a sense of what was going on. So, so I think, I don't know if we even said this in our paper with Mark, but the first space which was discovered to have the combinatorial Loewner property, but wasn't already known to be Loewner, was the square carpet. Mari and I were together at Michigan, and we're kind of grappling with all this stuff with Juha, and that was kind of the first case we looked at. And then that became the model for an argument that was applied in greater generality. And we had no idea how close that was to being Loewner, but it seemed like a fascinating question, also connected with the conformal dimension question. Yeah.
Well, I mean, the strongest support in favor of asking this question is the quasi-symmetric invariance of the combinatorial Loewner property, right? I mean, that certainly suggests that this is some of the right and natural condition.
Thank you. Yeah, thank you, Bruce. This was a very good addition. To the history. Yeah. So.
Sylvester, can I also ask a question? Is the round carpet example, that's a limit of a Kleinian group, limit set of a Kleinian group?
That's a limit set of a Kleinian group, yes. A reflection group, yeah.
Right. Well, I was under the impression that Mario and Bruce proved that these things don't attain their conformal dimension unless they are spheres. Am I wrong?
That's in the case where if they're homomorphic to S2. So in this case,
that's what I'm saying. Unless they're homeomorphic to S2 or even higher dimensional thing, they're not minimal. I thought that was one of their results.
That's right. But so in this case, it's a carpet-like space, so it's not the whole sphere. So it's different from that setting.
Grant, are you thinking about the cap-1 metric? Is that possible? That's another kind of line of discussion where you're looking at cap-1 metric, and then you look at the visual metric, cap-1 visual metric, and you ask if that attains the conformal dimension.
Maybe.
Is that what you have in mind?
Yeah, maybe. I think I just thought that in this case it was known that conformal dimension is not attained by this example, but I may be wrong.
But I think
Yeah.
it's a specific realization, right?
Okay. Okay. Yeah.
No.
But-
I mean, Grant, you're absolutely right. I mean, this was a theorem in a paper by Bruce and I, right? I mean, this two-sphere boundary paper. We have a more
Yes.
general result that says
Yes.
that, you know, if you're embedded and blah blah blah, you know, then you can only be entitled to very special assumptions. And for this round carpet model, this doesn't apply. So it does not attain, right?
But I think, unfortunately, I don't remember. I believe that same example or something similar to it is a limit set for a hyperbolic Coxeter group, and I believe there's some for which, right, that you do have the combinatorial Loewner property, right, as Sylvester's saying here in this slide.
Yeah, no, certainly you do have the combinatorial Loewner property.
Yeah. So the metric, so maybe to summarize it, so the metric that is drawn here, the cat -1 metric that you get, that embeds into the sphere isometrically, this is not minimal. So this is known. The metric drawn in the picture is not minimal. But well, you know, obviously know this because otherwise we could have the minimal. So, but then yeah, it's not known then whether there could be some other metric, not the cat -1 metric that could be minimal.
Okay, thank you. Sorry.
Yeah, no, I'm glad that there's discussion. Yeah, and thank you, Mario and Bruce, for these very good comments. Yeah, so I actually I should say that so for all the pictures that I've drawn here, we still don't know. I mean, they're combinatorial Loewner, and they could still be quasisymmetric to Loewner, and I don't yet have a firm belief for one way or the other whether they attain their conformal dimension or not. But what we do have is that this natural idea turns out to be not true. So this combinatorial Loewner property is not. So actually, I'm jumping a little bit ahead. So first of all, well, maybe I'll skip this because I'll get to this. So this turns out to be false. So there exists explicit graphs and so this is a divided talk, so Riku will talk about this more. I'll just state this result. There exist explicit self-similar fractals that are called edge-iterated graph systems that are combinatorially Loewner, but do not attain their conformal dimension and are not quasisymmetric to Loewner. They're explicit. You can draw pictures of them and visualize them. So here's one picture that will be explained more in the second talk. These are explicit. These have all topological analysis non-negative dimension 1, and they're homomorphic to the Menger curve. And if you want to know why these are examples or what's all going on, you'll have to stick around for the second half of the talk. But so this conjecture, at least as stated, or this question as stated, is not true. There's something else happening also. And I should say there's more work. So if you next month we'll have a talk by Madhav Murugan, and he will probably mention some work about the conformal walk dimension. And there are cases where we know that this conformal walk dimension is not attained. And there actually, interestingly, one also knows that for the Sierpinski carpet, it's not attained. So there's still, there's also this other side of the work. But so we now have examples where this is not solved. But there's this beautiful picture that many have seen from Matt Maita about the illustrated guide to a PhD, that what we've actually shown is we show that there's like this tiny little thing of things that are CLP, but not QS to Loewner. So we took, previously I showed that we understood like a small class of spaces. Well, now we were able to push this a tiny bit by constructing these natural weird, you can take your pick view of spaces. But there's this whole other world of these spaces, all the other examples, the Sierpinski carpet, boundaries of all the hyperbolic groups. So we did not answer Bruce's question for boundaries of hyperbolic groups. So this remains still open. And Matt Might tells that when you take his picture, you have to also remember to say this, keep pushing. So we need to keep going further. So there's still more work to be done here. I think this is still a beautiful question to look at. And so we have already done some steps. And I'll mention one thing. This is together with Guy C. David, about getting something that is more interesting. So in particular, something that is not topologically one-dimensional. And I'll also say that, so this example is motivated by this three-dimensional hyperbolic buildings. And but this is a slightly simpler example of that. So I'm hoping that understanding this could actually help also to identify some group boundaries. But at present, we only have this example. So the example here, I'll say a little bit, and because you'll see that. So there's a familiar loxo-type example where we start off from an interval and we double the central part, loxo diamond space. But now imagine you do this in 2 dimensions. This seems also, it's quite natural to look at this because it hasn't been somehow identified before. You start off from a square, you divide them into a 3x3 grid, and then you take this central square and you double it. And then you repeat this at every level. You get a metric space that is all-first regular. You can also show that it's not Loewner itself. And what's interesting is you can show that it's combinatorial Loewner. And this follows from actually a general sort of meta theorem that we showed with Anttila, that anything with sufficiently nice symmetry groups that is self-similar has the combinatorial Loewner property. This was essentially, this would also probably follow from Bruce's and Mark Baudon's work with modifications, but we gave a little bit more general statement and explicated these facts. So this space is combinatorial Loewner. You could ask whether it attains its conformal dimension. And what we discovered with Guy C. David is, well, we weren't not able to solve this, but we got a very curious implication. Namely, we were able to show that if this fractal space that we construct, if this fractal space attains its conformal dimension, or it is quasisymmetric to Loewner, then we can sort of push things down and we can get an exotic metric on the standard square, or by gluing or blowing up, we can get it on R2 or the standard sphere. So we get a metric and measure on the standard sphere, which by necessity, it has to look very non-Euclidean. And as a consequence of this, we can show that it has to have a so-called one-dimensional cotangent space bundle. So this is called a one-dimensional, we call this a one-dimensional sphere. So if this space upstairs, this X, attains its conformal dimension, then you have a one-dimensional sphere, whatever this means. So we were not able to answer either of those questions, but this implication is interesting because either it gives another example and another way of showing that you're not quasisymmetric to Loewner, another abstraction, or it gives you an example for an entirely new type of analytic structure on the sphere. So I think both of these are, of course, both can turn out to be false, but so that's a possibility. But and what does this analytic one-dimensional condition? I can state it just so that you have a little bit of a grasp of what it means and how weird it would be. Namely, you can state it in the following way. So you have some metric, and this time also a measure on the sphere. And this measure really should give you a Poincare inequality, but because I didn't want to define it, I'm not saying anything about it. But the condition is that all pairs of Lipschitz functions are linearly dependent. So for every f and g, at almost every point, f is a a multiple of g, or the other way around. And so there's one-dimensional space of functions, up to a little o of distance term. Now, how this connects, so I mentioned that this downstairs metric would have to be strongly non-Euclidean, and where this one-dimensionality comes from is from some work of Bruce Kleiner and Guy C. David, that if you are a planar differentiability or PI space, then you have two options, roughly speaking. Your analytic dimension, this cotangent bundle, is either two-dimensional, in which case you are essentially you're rectifiable, and then you come back to the almost directly back to R2 standard metric, or then you are this exotic one-dimensional thing. And they also pose the question whether this one-dimensional thing exists. So we don't know, but it seems somewhat pathological. So if anybody has ideas, this would be a wonderful thing. But yeah, this is the last thing I have here. So thank you for your attention. And
yeah, thanks, Sylvester. So let's thank him. And let me start the discussion. So are there any comments or questions?
Sylvester, this is a really vague question, but it's nice to, optimize and find minimum of things. And maybe the Hausdorff dimension is not the best thing to optimize. Maybe there are quantities, for instance, if there was a way to quantify how Loewner something is, then one could try to optimize that instead. I don't know. It's vague. Sorry.
Well, I think you're onto something. I mean, I won't say something because this is also a topic of ongoing research, but it's maybe partly related to this third point that there are also other notions of niceness, especially related to potential theory. And one of these is this conformal walk dimension, and it's related to this picture. In this case, the space, the Hausdorff dimension minimization is not attained, so it's not quasi-symmetric to a one-dimensional space, which is one all-force regular, but its conformal dimension is 1. But there is a different attainment problem that is reached, namely by this harmonic gasket. There are some ongoing discussions, but about also that there might be a family of this type of attainment problems related to potential theory, but we still, yeah. So
there are other comments or questions?
Yeah, I had one question as well.
Go ahead.
Well, first of all, very nice talk, Sylvester. My question was about the last example, the pillow thing. So are there any bounds that that, like, does it follow from Keith Laxo that it's not minimal?
So this example or the
No, the very last one, the pillow thing. With the
yeah.
middle.
Okay, thank you. Yeah, good. I'll just go there. Yeah. Essentially, it follows from Keith Locke, so that this is not so. Well, we do it a little bit simpler. We show that this is not a Q. This is not Q Loewner. It doesn't satisfy a Q Poincare inequality, and then therefore it's minimal. You could also, if you want to suffer, you can probably show that the Q modulus of all curves vanishes, but we did not do that. So we used the observation that, actually, I'll explain it in this case. In the Loxo diamond case, it is a Poincare inequality. It does satisfy a Poincare inequality when you put the right measure, and also for the pillow space, it actually does satisfy Poincare inequality when you put the right measure. But if you put the all-force regular measure, it doesn't. And the reason for that is that when you take the all-force regular measure and you push it down, and what happens is that the measure will distribute unevenly. So upstairs, there are 4 pieces. So on the left, you have 1/4, and then on the middle, you have 1/2. And you get this fractal measure, which has to be singular with respect to Lebesgue measure. And this is known that this one Lipschitz function, its image cannot be singular. So we use the same fact with Geisy-David to conclude that this cannot satisfy Poincare. And by what I said before, that the attainment problem and the Loewner problem, these are equivalent. So if this already attained it, then it would be Q Loewner, which it's not. So therefore, yeah.
And are there some non-trivial lower bounds?
2, because it contains R square.
Yeah, that's what I said. I meant like bigger than 2 or no.
I think you can get some lower bounds by constructing some flows, some natural flows here that split in the middle. You compute the energies of them, you'll get some non-trivial lower bound. Yeah, Riku has done some of these calculations. I think you can maybe correct me. It was pretty close to 2, right? The pillow space.
So, but it's bigger than 2, right?
Around 2.08 or something like that. Yeah. So yeah, it seems to be close to 2. I mean, yeah.
So what is your sense? Will the Loewner metric in this example or not? Or is it just possible to...
I have extreme difficulty of imagining what a one-dimensional sphere, what the structure would look like. So because of that reason, I'm skeptical, very skeptical that it could attain. But I don't think it's out of the question still that in some cases, some non-trivial cases, this combinatorial Loewner condition would actually imply a Loewner condition. So, and maybe this technique, this idea of using the combinatorial Loewner condition, identifying some right construction of a metric, maybe this can succeed in some cases. But so all I know at this point is that it doesn't succeed in all cases, and maybe this pillow space is also not. Yeah, but yeah, I mean, Guy maybe disagrees with me and hopes that this will give would attain its example, and then give a very nice example of a PI metric on the sphere. But I don't. Yeah, my intuition says no, but yeah, could be completely wrong. Yeah, as Guy comments in the chat, this is a hope, not a conjecture. So. I won't state a conjecture either way, but I say that it's worth thinking about because it has this. So.
Okay, so do we have other comments or questions? Well, let's thank Sylvester again.